Good morning, dear students. Today we are going to see about low power system on chip design. Okay, low power system on chip design. That is how we can able to design a system on chip with low power consumption. Okay, so we know as the integration scale increases, the power efficiency or power efficiency and performance per watt become more critical matrices along with the absolute performance of million instructions per second. We know we are using a single integrated chip, that is at a time they are performing millions of instructions per second. Okay, so we need more power efficiency and performance per watt. Okay, so low power system on chip is essential to achieve high power efficiency and performance per watt. So this system on a chip, it is necessary. So just to concept the power, we need this system on chip design to concept to become power efficient and performance efficient. Okay, low power design methodology have been well developed now and are actively employed in the design of system on chip for cell phones. We know we are using mobile phones, and at a time we can able to in a single charging only we can able to use the mobile phone for many hours, right? So these all will be carried out only by using this system on chip design. Here, first one, CMOS circuit level low power design. Okay, the first step to low power design is to know the source of power dissipation. The design then can be achieved by the reducing the contribution of each source by all means. First, First is to identify the source of power dissipation, that is in which parts the power is consumed more and in which area the power is consumed low. That all we have to identify first. Okay, then the design can be achieved by reducing the contribution of each source by all means. Okay, this figure just shows a CMOS inverter and a short circuit current. Okay, so the CMOS logic device consume power when they are operating. Okay, so it will consume power when they are in the operating mode. Okay, there are two major sources of active power dissipation in the digital CMOS, that is dynamic switching power and short circuit power. There are two modes of power dissipation in this, that is dynamic switching power as well as short circuit power. Another power dissipation source is the leakage of power that results from the leakage. Here, that is normally in this CMOS technology there will be three sources where the power dissipation is carried out. That is in dynamic switching power, short circuit power, and the leakage of power that results from the sub-threshold current of the current flowing through MOSFET. So the total power is given. Okay, P total equal to P switching, that is dynamic switching power, then P short circuit, that is short circuit power, and P leak, that is the leakage power. Okay, the first term denote the dynamic switching, that is CL is the loading capacitance, F clock is the clock frequency, and alpha 0 tends to 0 is the probability that power consuming transmission occur. That these comes under the first one, that is the power of the dynamic switching. Okay, and the second one is the short circuit power, that is calculated as ISC into VDD. What is ISC? That is the short circuit current. Okay, ISC is the circuit current. The second term is due to the direct path short circuit current ISC, which arise when both NMOS and PMOS transistor are on at the same time. So when this NMOS and PMOS circuit will on at the same time, this will occur. Okay, and the third term is due to the leakage current. Usually the active power consumption, especially switching power, that is P switching, is dominant, but for 90 nanometer and 65 nanometer CMOS fabrication process, the leakage current is almost 30% of the total power consumption. So now, okay, that just the power consumption, the amount of power consumption. The low power design methods are ways to decrease the power dissipation by reducing the values of this alpha 0 tends to 1, CL, VDD square, and F clock. Okay. So this low power design is mainly used to decrease the power dissipation by we can reduce this values alpha tends to 0, CL, loading capacitance, F clock. What is F clock? Clock frequency and all. Okay. So for low power interconnection, the signal swing is reduced to decrease not only the power consumption but also the charging of time of the interconnection. Capacitance, which will be explained in more. Next, architectural level low power design. Okay, there are many low power schemes that have come up from the level of RTL design, register transfer level design. Most common and widely used method is clock gating. That it is just in this architectural low power design, we are just discussing about a method called clock gating, which disables the unnecessary block in the synchronous system. So the clock is connected to the internal circuit, that is just clock gating. That is just it is a low power scheme for the system on chip design. Okay, so through this AND gate, okay, through this AND gate, which is controlled by the enable gate signal, this that is the clock is connected to through this clock signal is connected through the AND circuit or through the AND gate. Okay, and this other end of the AND gate is connected to the enable signal. This scheme can be applied block by block to selective control power consumption. So this is the method. So for each unit we are giving a clock signal, and this clock signal consists of a clock as well as an enable signal and given to the each unit. Okay, so in this when the clock is high, the clock enable signal goes high. In this case, the pulse of the first clock signal is not wide enough, which may lead to difficulty in the circuit operation. This can be avoided by using a latch to make the control signal high only when the clock is low. Okay. So if both the signals are in high position, means we can't able to the pulse of the first clock signal is not wide enough. So this can be avoided by using a latch to make the control signal high only when the clock is low. Okay, it is shown in the above figure, clock gating circuit. So in the architectural level, parallelism can be utilized to reduce the power consumption. The power consumption is carried out by using a method called parallelism. That is, if you put the same functional module in parallel with one original one, you can double the throughput of the functional operation and as a result lower the clock frequency by half. If we connected these circuits in the parallel, means we can able to double the throughput of the functional operation. As a result of this, the power lower the clock frequency will be reduced to half if the throughput is same as the original one. So the pre-computation can remove unnecessary toggles too. Before the entire operation of the main circuit, a part of the circuit is pre-computed. The internal switching activities of the main circuits are controlled by using the pre-computed result to reduce the number of toggles. Okay. Then next one, system level low power design. So in the system level low power design or subsystem has one or more major functional modes. That is, here in this we are going to discuss about various modes, that is ideal mode, operational mode, sleep mode, power down mode. In the operational mode, SoC operates as the normal function. Okay, it will just operate as a normal function. In the ideal mode, the clock buffer is on, but no signal is being switched. Ideal mode, clock buffer will be on and no signal is till now being switched. In the sleep mode, the clock part as well as the main block is off when the SoC is turned off with the power supply is connected. So in this sleep mode, the clock clock part as well as the main block is off. And in this power down mode, when the SoC is turned off with the power supply connected, it is in the power, the SoC is turned off with the power supply connected. In the system level, low power solutions are multi-supply voltages or voltage scaling, power shutoff, adaptive voltage scaling (AVS), and dynamic voltage and frequency scaling (DVFS), dynamic voltage and frequency scaling. These are the low power solutions for this one, that is the DVFS, adaptive voltage scaling, power shutoff, voltage scaling, etc. Okay. Then for the system level low power schemes, the SoC is first divided into multiple voltage and frequency domains. So for this low power scheme, the system on chip design is first divided into multiple voltage and frequency domain. The figure below shows the example of the cell phone application. Here, processor with 20 different power domain is connected in this. Just have a look on this. It is not necessary for the exam. Okay, just have a look just to understand it. They given this. Okay. So the separate control of the power dissipation in different power voltage level requires a level shifter and isolation cell or micro input output and a micro switch to supply the controlled power to power domains. The different power domains, the different power domain interference is shown in this figure. In addition, attention should be paid to cross-domain timing closure, which represents the variation of the signal delay time and its related trouble in circuit operation when the signal travels over the boundary of the voltage domain. These are all just an example. Okay, you have to just go through this. This shows the delay variation due to the multiple voltages. Then shifter circuit for power dominant interfaces. Just have a look onto this. Okay, and okay, so the operating system controls the schedule according to the workload of different domain. Based on the workload, the scheduling will take place, and when the voltage and frequency decreases, first the clock frequency and then VDD are scaled down. In contrast, for the scalper, VDD is up first, followed by the clock frequency. It's just a figure showing this rush current control with the buffer chaining. Okay. Then trends in low power design. There are 4 basic themes for the low power techniques: trading of area and performance for power, adapting design to environment condition or data series, avoiding waste, and exploiting locality. It is clear that the power can be traded with performance and the area can be used to recover the power. As we have examined earlier, lower voltage leads to lower power consumption with slower operational speed. According to the variation in the environment or static of the input data, The operation of the circuit can be dynamically changed to safe mode. DVFS is an example. Avoiding waste is a very effective technique. Clock gating and power shutoff of the good example. Okay, so for this low power consumption of the system on design, mainly we have to concentrate on clock gating and power shut off are the good example. In addition, charge recycling reuses the power without waste. Exploiting the locality is another techniques of low power. A design partition to take advantages of the locality can minimize the cost of expensive global communication and exploit the partial activation of the chip. So charge recycling reuse the power without waste. Okay, so mainly the clock gating and the power shut off are the good example of this. Okay, these all comes under this topic, low power system on chip design. Just have a look on through this. If you have any doubt, you can ask me. And in the first topic, there is one topic you have to study by yourself. I will give you the notes, and if you have any doubt in that, you can ask me just based on the scheduling and it is coming. So it's the end of the first unit. Thank you.